Thanks, Mark. It's my pleasure to introduce our CVR Vista seminar speaker for today, Dr. Aaron Hertzmann. So just a quick note of kind of the usual housekeeping for Zoom seminars like this. I would ask everyone to please keep their audio muted for the meeting unless you are specifically asking a question. There will be opportunities to ask questions at the end and potentially, depending on what Aaron decides to do, to ask some questions in the middle as well. When that time comes, the easiest thing to do is to either use the kind of raise hand option or to make comments in the chat, and I'll be moderating to try to keep an eye on that and call on people and unmute them or relay the chat questions in the event that that's where questions get posted. But otherwise, please keep your audio muted. You're welcome to keep your audio on if you'd like. It's often entertaining as a presenter to actually get to see what people are thinking, although sometimes depending on your setup, you may or may not be able to see it. So it's entirely at your discretion. Okay, so with that little bit of housekeeping covered, let me just give a quick introduction to Aaron. I've known Aaron now for, I don't know, 17 years, something like that, 16 years, a while. He's currently a principal scientist at Adobe Research and an affiliate professor at the University of Washington. He has a distinguished career in a number of areas in computer graphics, computer vision, machine learning, HCI, number of areas. He's an ACM fellow, IEEE fellow. He's currently editor-in-chief of Foundations and Trends in Computer Graphics and Vision, and as well as having editorial roles on a number of prominent journals and graphics. His background is quite interesting, a bachelor's in computer science and art history from Rice University and a PhD from NYU. He spent 10 years as a professor at University of Toronto, and while he's currently at Adobe, he has also spent time working at Pixar and Microsoft. He's published numerous papers in areas mentioned, working on stylized rendering, data and physics-driven character animation, and lots of other interesting technical topics. And he's also written very recently a number of really interesting articles and blog posts and done a number of talks on kind of perception of art and the role that computers and AI play in art. I believe some of that will be the topic of the talk today. But if you haven't seen his articles and whatnot on the question of whether or not computers or AI can create art, I strongly encourage you to check it out. I've been greatly looking forward to this seminar myself since I heard that Aaron had agreed to graciously come and speak, and so I hope you all enjoy, and I will pass the baton now to Aaron. Take it away.
Great, thanks so much for the kind introduction. I'm not yet able to share my screen, so I need that ability in Zoom. But yeah, I wish I was visiting York in person and see a lot of familiar faces in the audience and new ones as well. It's too bad we can't discuss it in person. Looks like now I'm able to share. All right, so I've hit share and hopefully my slides are either visible or they're coming up shortly.
Aaron, I think you'll need to stop sharing on your side. There we go.
Okay, and so if there's a theme to this talk, the main theme I want to talk about is how computational models, especially in computer graphics and computer vision, can inform how we understand our perception of art. As you know, there's many different ways to understand art, all of which are quite useful and valuable, from psychology and sociology and culture and art history. And I'm sure I'm sure everyone's here aware of the long history of how neuroscience and vision have influenced computational models of computer vision and vice versa. And here I want to just sort of provide two more ways I think that these perceptual models can help us understand art as well. So hopefully you should see my slides now, and if not, let me know. Otherwise, I'll just plow on. There's two parts to the talk. The first part is specifically on line drawing, but it's sort of more broadly about realistic depiction. And the second part is more about abstract and contemporary art, and specifically focusing on ambiguity in art. So hopefully that covers enough territory. And I was thinking, just as an experiment, I'll stop for maybe 5 minutes for discussion or just 2 or 3 questions after the first part, because the two parts are quite different from each other. So starting with line drawing, I want to begin with the assumption that our visual perception is optimized for real world scenes. Like the reason that we have a visual system is so that we can survive and navigate and understand our natural world. And so this has been this long-standing question in psychology and philosophy that line drawings are not a real world percept. We don't see them walking around in the real world. And so why is it that we are so good at perceiving shape in line drawings and recognizing objects when there's no reason why we should be evolved to do so? And so like one natural idea that's been around is that depiction styles are learned, that we learn how to understand line drawings in the same way that we learn to understand written language. But this, to me, this seems implausible, just part of gut feeling. Also the fact that line drawings seem so common throughout history, throughout different cultures, and even before pre-civilization, we see things that look in some way or another similar to line drawings. And in fact, there are some, there's been a variety of studies related to this. I guess this one by Hochberg Brooks, it sounds like it's relatively famous, where they raised their son for his first 14 months not to see any pictures at all. And then after 14 months, when they couldn't keep it up any longer, they showed him this drawing and he said it was a car. They showed him a photo, he said it was a car, and so on with a variety of other pictures. And since then, there's been a variety of more rigorous and more, more rigorous studies on a variety of different groups of individuals who had not been exposed to pictures and civilization, and they could all basically recognize objects within drawings as well as photographs. And there's also some limited studies with chimpanzees as well that show something similar. So there's a lot of evidence that someone who's never seen a line drawing before can understand it. And so that's the context in which I want to talk today. There's also some evidence that line drawings are processed by the same neural pathways as natural images. For example, our recognition ability and recognition times are similar between photographs and drawings. And there's fMRI studies that also suggest the same thing. There's been a lot of study in the perception literature about the geometry of occluding contours. So if you know where the occluding contours are, what information do they contain? But these studies don't tell us why we should be able to understand the occluding contours in the first place as lines. So what I think is sort of the conventional wisdom in this area is the notion that line drawings work because they activate edge receptors. So we know that lots of times if you run an edge detector on a photograph, you get a line drawing. And we know that the visual cortex includes edge sensitive cells. And so perhaps these edges in line drawings are activating the same cells as the corresponding photograph. And so I've only found one paper that actually attempts to articulate this theory by Sayim and Cavanagh. And in this paper, they point out many issues and holes in this theory. But whenever I've discussed this question of line drawing with people in vision and human perception and neuroscience, quite frequently they bring up this theory. And in fact, this is what I thought decades ago, and I cannot remember where I've heard it. I feel like I have only found this one paper, and yet it seems like this is a very commonly held view. And I'd be interested to hear if anyone has other citations related to this. So I see there's being kind of three problems with this view of line drawing. The first one is that the contours of many natural images don't correspond to line drawings. For example, when you have cast shadows, they produce contours that you wouldn't normally draw on a line drawing. Now, this first problem is actually, I don't think it's very significant, and the theory that I'll describe later provides a solution to this. What I think is the real problem, so the first is that vision is more than just edges. We can tell the difference between these two images or the two images on the right. We can tell the difference between a line and a filled-in region or step edge. We identify color and texture, and it just seems like this idea that somehow that the fact that some edge responses line up with some of the edge responses in the photo, and we ignore all of the other features, to me, this just seems implausible. Partly because our vision system is so robust, why would we be fooled by such a weird percept? And moreover, just to illustrate the fact that vision isn't just edges with these moony faces, these are examples where our perception from the edge image is really, really different than our perception from the corresponding photograph. So there are cases in which we do care about the other features in the image besides just some subset of the edges. The other issue is a little bit more philosophical. A lot of this discussion kind of presumes there are line drawings and there are photographs. We just have to explain how how we can understand these two kinds of things. When in reality, there's no clear separation in artistic styles between line drawings and photographs. There's really, I think, an infinite, a continuum between these different styles. You can add a little bit of hatching, you can add a lot of hatching, you can have a little bit of sketchy strokes, you have really sketchy strokes, a bit of color. There's just so many different styles by which artists depict things that we're all able to interpret in various ways. Maybe some of this is learned, but it still somehow seems connected. And somehow it feels like, whatever theory will explain our ability to understand realistic depictions, that theory ought to include edges on line drawings, but the edge-based theory alone can't explain any of these other styles at all, because these all have edge responses really different from natural images. So a more general theory, I think, is needed. So the first kind of, before I get to my actual proposal, I want to start with the hypothesis that line drawing perception is a consequence of realistic image perception. So you should be able, so a system that is capable of doing human level, robust shape perception from a single image ought to be able to also correctly perceive shape in line drawings. And I actually wrote this in a first draft of a paper I submitted on this topic, and the reviewer said, well, you should try it. And I didn't really think it was worth trying. I didn't think it was going to work because our current vision algorithms are not human level, and they're not as robust as humans, but the reviewer said so, so I felt like I should try it. So I grabbed a trained model from one of the state-of-the-art methods. So it's a deep convolutional neural network that was trained on pairs of photographs and depth images. I'm oversimplifying a little bit, but this is basically what it, it's supervised depth estimation, trained only on photographs, and it works quite well. And lots of photos I plugged into it. Qualitatively, it seems like it's getting the relative depths and silhouettes more or less accurate. And when I ran it on some line drawings, here are the results I got. And I was surprised. It seems like it's doing roughly as well as it did in real photographs qualitatively in terms of getting relative depths. So that to me seems like there's support for this hypothesis that perception of certain kinds of line drawings is a consequence of natural image perception. And it's far from perfect in the ways that the system operates on, comparable to the results on real photographs. And there are photographs for which, or drawings for which it doesn't work, but these are also scenes that are outside of the domain of its training data. So the network was not trained on, Phaeton, riding his chariot through the sky. Okay, so then the question is, so our goal should be, how do we explain line drawing perception in terms of realistic image perception? So given a viewer that is capable of understanding shape in natural images, why would they understand line drawings? And before I give my proposal for this, I'm going to take a long detour into the field of non-photorealistic rendering, which is a subfield of computer graphics. It's a lot of my work has been in that area, like my PhD was in this area. And so in non-photorealistic rendering, we develop computer graphics algorithms that can take, for example, a 3D object and produce a line drawing of that object. And for some reason, this image disappeared here. So we have this large collection of algorithms developed over the decades that can produce lots of different really nice artistic rendering styles from 3D models. And some of these algorithms showed up in video games and in movies. And I would argue that, in a sense, this all this research together formulates a generative model for representational art. It's not how artists work, but it is a representation of the space of artistic styles that representational artists can produce. And like any model, it's incomplete, but useful. And so the sort of the building block of a lot of 3D non-photorealistic rendering are the occluding contours from, originally from vision and perception. So for this object, the occluding contours, we can draw the occluding contours to get a cartoon rendering, and we can stylize them to produce a sort of stylized version of the 3D model. And the conventional formulation of the occluding contours, which is not important for this talk, but roughly it's the set of, on a smooth surface, it's a set of points at a grazing angle to the viewer. But there's actually another formulation of the occluding contours which is more useful, and this is as follows. We'll take our 3D scene, and make every object, get rid of all texture, paint every object with white liberation or diffuse materials, get rid of all the lighting except for a headlight, which is so like a light co-located with the viewer. And then so we get this rendering here where the reflectance at a point is n dot v, so the surface normal dot the view vector. And in this rendering, the occluding contours are the set of points where n dot v equals 0. So that's a set of pixels which are completely black in this image. And if we trace our pen through those black pixels, we get the occluding contour rendering. So we get, it's a beginning line drawing. It's a little bit empty, but notice there's this additional ridge, this sort of valley of dark pixels here, which is we could have extended the curve further. And if we do extend the curve further, then we get what's called these the occluding contours, is this additional curve here, and that produces this rendering. And this rendering is a lot closer to what starts to look like a natural line drawing. And moreover, we can also thicken these curves by the thickness of the sort of the dark bands in the diffuse rendering, and then we get, I would say, even a nicer rendering. So you can see the image on the right as being sort of an approximation to the image on the left, or maybe it's an image which preserves the dark valley features of the image on the left. So there's some commonality between these renderings visually. When we apply this model to other objects, we also get sort of plausible, not perfect, but plausible sets of lines. And there's a few ways we can evaluate these things. So one simple thing my student did was to create a 3D model based on the object on the left, and then animate the model, render it with one of these algorithms. And you can see that it generalizes pretty well for an algorithm which has 2 or 3 parameters. No, this is no machine learning, it's just all hand-tuned. A much more formal and rigorous evaluation was performed by Forrester Cole, where he asked a collection of artists to create realistic line drawing depictions of a set of 3D models with known shape. And they found that these kinds of algorithms can predict where people draw lines with reasonable accuracy. Not perfect, but certainly enough to believe that we're on the right track, that there is some predictive power in these kinds of algorithms. And just as an aside, I'll mention we have a CVR paper recently that does use machine learning in order to clean up these drawings and to make even more high quality renderings from them. So with that background, I can then suggest one possible framework for understanding how line drawings work. And this was a paper that I published in Perception earlier this year. So again, we'll start with the assumption that our perception is designed or optimized in a way for real world scenes. And it's also very robust to various forms of corruption. And so the main hypothesis here is that the human visual system interprets the line drawing in the same way as it would some corresponding realistic image, or with similar features as some realistic image. So when you see this line drawing, there's some rough correspondence with a corresponding realistic image. And even though that particular lighting setup I mentioned is not common in the natural world, it contains elements which would be. So we have this potentially familiar geometry, liberation of white materials, a point light source with this particular arrangement. Even though this combination of elements may not be typical for the real world, all of the elements are, and we are very capable of understanding unfamiliar arrangements of familiar phenomena. So in some sense, the observation is that these two images are roughly perceptually similar in some way. And it doesn't necessarily have to be this particular Lambertian rendering model. Hopefully you're still seeing my screen as I adjust my layout here. If, for example, we can take this object here and adjust, crank up its exposure, we get something more and more like a line drawing. This might also correspond to increasing the glossiness of the material, adjusting the lighting conditions in various ways. So I don't want to commit to like this is the particular rendering model. It is a proof of concept that there are rendering models that are similar to line drawings. And there's also evidence that there's certain kinds of lighting variations that we're not that sensitive to. So there is some flexibility in what the actual lighting and rendering model might be. This also suggests a way of thinking about essentially representational art as being inverse vision. So suppose you're an artist and you're capable of drawing thin line drawings. You're sort of restricted for whatever reason to only outline drawings and no hatching or stippling or paint colored paint strokes. And you have in mind some 3D scene you want to depict. So there's an optimization problem or an inverse problem, which is what is the set of lines you should draw such that a viewer capable of understanding realistic scenes should infer the shape as accurately as possible. And this basically says that line drawings are a solution to this problem. And this also suggests directions towards modeling artistic styles through an optimization process. And there's been some work on this in the sort of graphics literature, but there could be a lot more. So all the discussion so far is I've completely focused on contours of smooth objects, but there's really a lot of different types of lines in which artists draw on line drawings. And so now I want to suggest how some of these other kinds of lines can also be interpreted through realistic rendering models. One kind of variant that we see are white lines in a dark background. And I would explain these through rim lighting. Rim lighting is a photographic technique where you have cameras roughly to the side of the object. So these are all photographs, mainly by professional photographers. And they look very much like these inverse occluding contours or inverse line drawings. And for me, I am definitely not a unbiased observer, but for me, I perceive the object on the right as being more like a white ceramic object with attached shadows, and the one on the left is more like a dark glossy object with some lighting on the side. But again, that's just, I'm not an unbiased observer here. Hatching is another kind of lines people draw, and I think it's fairly easy to see how this kind of hatching rendering could be viewed as an approximation to a realistic rendering. Creases are a little bit more of a challenge to explain. So by creases, I mean C1 discontinuities like you'd see on the edges of a cube or a rectangle. I have a couple of different possible explanations. I can't really say that one is more compelling than the others. And in the interest of time, they're a little bit subtle. I'll refer to the paper, or I can discuss some more if people are interested. One possible explanation is that these are completely learned. To my knowledge, there's no studies that have been done to test whether someone who's never seen a line drawing before could understand these edges. They might be able to. So there's a whole range of possible explanations for them. And just more broadly, there's the research question is how is it we're able to perceive shape and identity in so many artistic styles? And to me, that's really the real question. It seems like somehow for future work that we're able to disentangle style in these scenes and understand objects and have some sense of what's going on in the scenes, even though we may have never seen this particular artistic style before. And that seems like something we're capable of doing, and something that I think is relevant for line drawing as well as for all of these other styles. So at this point, I think I want to pause for a moment, and I'll try to open up my chat window. Maybe we could just take one or two questions or comments in case anyone has any at the moment. And if not, we could also have further discussion at the end.
Got one if no one
Okay.
else does. So I'm just curious. So shading and occluding contours, they were in prehistoric drawings, where you say maybe creases are learned. Certainly, perspective was learned. It took us thousands of years to learn it. Do you think that's because shading and contour are more basic features, or do you think it's actually the other way around? We just don't have awareness of those other features, and we actually have some awareness of the shading and the contour.
Sorry, I missed the first part of the question. Yeah, I missed the first part of the question.
So it's obvious that even in prehistory we had access to contour and shading, and we could reproduce those in drawings, right? But it took thousands of years to learn perspective and maybe creases and things like that. So you could think of a couple reasons for that. One would be that we just have more awareness of the shading and the contours and that, or the other would be maybe that shading and contour are just more basic primitives that we're more easily able to represent. I'm just wondering if you have feeling for in your theory?
I think so. Artistic style is definitely something that which is developed over time. That you culturally we learn these techniques, and so like linear perspective is something that was a technique that had to be developed, even though it's perceptually very obvious why it ought to work. And then like this is even something like Gombrich, the famous art historian, talks about. So it's a little bit hard to disentangle because we don't know if you showed somebody for all these different artistic styles we have now, to what extent could they be understood by somebody who has never seen it like that style before. Yeah.
Thanks.
So Aaron and Marcus, this is James. I don't know if I can raise my hand, maybe because I'm a co-host. I don't know.
Well, if you put any of the indicators down at the bottom of the participants list, we can see you. But I think actually Patrick has his hand up, and I think if we have time for one more now, that'd be.
Yeah, thanks. I just had a question about creases, Aaron. It seems kind of a bit arbitrary to pick on poor creases. I mean, creases are just like folds, or it could be a rope or a branch, or a crease in a surface, a front edge. And they all seem to be pretty well described by some linear change of brightness. Or why would that be different from everything else? It seems I'm not sure why you're picking on creases.
So hopefully you can still see my screen. So I think for occluding
Your screen
contours,
is not shared right now, Aaron, just
oh,
by the way.
okay. Okay, good. Thank you. All right. Yeah, so you should be, so I'm sharing now. So for occluding contours, I think they don't really require separate explanation, because they could be viewed as sort of approximates to very high curvature smooth contours. And so a rendering of this object in the Lembertian setup I described would produce these creases. For the interior ones, that doesn't work. So the question is, what other realistic lighting setup would produce the rendering on the right from the image on the left? And that's what I have a whole bunch of these other slides as being possible explanations. They could be markings on the surface. They could be something you have to learn. They could be shadows under a very peculiar geometric setup. Did that answer your question?
In a way, but certainly in the physiology, the creases get as much priority as the occluding edges. It's all just in terms of contrast. So in physiology, there isn't any distinction made. Contrast is contrast, I think.
Sure. Right. So in the low level vision, and so I guess my discussion here is really purely about the completely high level view of vision without regard to the underlying mechanisms. So why would an ideal observer essentially understand these things? So I think what happens in the visual cortex is not recognition. So that may be less informative, I think. So I don't know if that addresses your concern or not.
Well, that's
I don't know who had their hand up, who was next, James or Kevin.
Okay, well, maybe I'll ask a question. So you motivate the model by an observer who's wearing a headlamp, basically, right? That's quite an unusual lighting condition, I think, statistically. And you point out that you don't have to draw with a black pen, right, to make a convincing line drawing. So I always thought, a natural explanation for line drawings is that at the occluding contour, the surface is very oblique to the observer. So as you move a differential amount in the image, you move a lot on the surface and change attitude very rapidly on the surface. And so statistically, you tend to get a lot of sunlight change events, irradiance change events, projecting to the image at occluding contours. So it could be, as you say, a shadow, could be a highlight. And maybe that's kind of what you're saying, but you haven't sort of said it explicitly. And that would also map to the folds, right, the creases as well, even though the attitude is not oblique to the observer, but it's the same sort of family of explanations where the surface is changing rapidly, and so statistically in the world, you tend to get a lot of punctate light events there. It could be shadow, could be interreflection, could be specular highlight.
Sure. So yeah, so that's sort of, I think, maybe related to, I guess, so this is the one possible setup in which you see lots of sort of lighting events, shadow events at the occluding contour. There's certainly other ones that would also produce these. So, it could be that it's not the specific arrangement that really matters, but that on average for this object over a range of possible lighting conditions, you would see lots of occluding contours. I think, yeah, so even though you mentioned that this is not a common arrangement, but I don't think it's important that the arrangement be common. It's that we're capable of understanding scenes with all sorts of lighting arrangements. Any individual arrangement might be low probability, but we can handle a whole range of lighting conditions.
This is one very specific lighting condition. So that if we stick with this theory, we only so the idea is that whenever we see a line drawing, we always think, oh, this is that unusual case where we're wearing a headlamp. And that, yeah.
Well, you could pick any other photograph and say this is also an unusual case that the light happened to be at that one particular location out of all the possible locations it could be at.
Yeah. Yeah. But it seems like, I guess, so the claim might be that the critical factor is the foreshortening. It's the compression due to projection.
I wouldn't say it that way, because I mean, my goal here is to explain how you could produce a realistic image that looks like a line drawing on the belief that we perceive line drawing. So I think just the fact that there exists a object gradient is not enough, because object gradients don't always translate into rendering effects or dark patches against a light background. I mean, I think it's very related to the idea that what I describe as what I view as kind of the conventional wisdom, that the fact that edge detectors fire at places that tend to be drawn as lines is the explanation. And that doesn't really explain why this image on the right should be understood by a system designed or optimized or whatever to understand natural images. Because this is still not a natural image, without what I'm describing.
I think maybe we'll do one more question now and then we can carry on. And of course, if there are more questions or more discussion around this, then we can pick that up at the end. But Kevin, I know you've been waiting patiently from the start of the break, so.
Thanks. I guess first, have you read John Willott's book, Art and Representation?
I've only skimmed it, just in particular one chapter I was interested in. I haven't read the whole thing.
So he has work that does similar things with generative modeling of line drawings to try and account for different kinds of pictorial styles. But one of the things that he does is he covers all the different types of projection systems. So we mentioned a bit earlier that linear perspective took a while to work out, like throughout, a great deal of Chinese and Japanese art up until the 19th century was in parallel projection. So instead of having the railroad tracks receding in the distance looking like converging lines, there would be parallel lines going towards the top of the image. If you look at like the developmental trajectory of drawings among children, you see that linear perspective comes really late, but very early on. Line drawings, the lines don't depict occluding contours, they don't depict edges, they depict regions. So you get stick figure style drawings early on. If you're trying to draw a table from the side view, the tabletop looks like a square. So there are all these ways of using lines to depict scenes that are completely different than anything like perspective optics or contours or lines as contours, but which seem to be really naturally interpretable and easy to interpret without too much learning. In fact, very early on in development, people seem to do this. So I'm wondering how that fits in. I saw later you have a diagram of engineering drawings. So that's a similar sort of question. How do we interpret these drawings which really don't operate according to perspective geometry and where the lines are denoting something really different than contours or edges?
Yeah, so I think those are sort of two separate questions. So I think, and this is all conjecture. Obviously, I don't know for sure. I think with respect to like architectural or blueprints, topographic maps, these are just you have to learn how to read these. They're not things that you can pick up immediately. With respect to development, I think so in general, I think there's a common theme in a lot of this discussion literature, this assumption that the way you draw is the same as the way you perceive. And I don't think that that's necessarily true. The strategy is like, I think learning to draw is learning motor programs and learning strategies for depiction, and as well as developing artistic style over the centuries. We are learning strategies and experimenting with things, and that is distinct from what the perceptual process is. So, I mean, I don't obviously no one knows for sure how these things relate, but I would guess that to understand the way children draw, we have to understand these learning strategies and motor programs and so on, which is distinct from understanding perception.
But just
and
a
there's
brief
a feedback
follow-up.
loop between those two things. I'm sorry?
Just as a brief follow-up, one, so I guess maybe fair enough about the architectural drawing. I'm not fully sure, but I'm wondering about like parallel projection systems. Thousands of years of Chinese and Japanese art which aren't following linear perspective, but it seems implausible to me that those had to be learned in a way that you had to learn to perceive those in a way that you didn't have to learn perspective. And similarly with the feedback loop that you mentioned in development, a kid needs to at least be able to see what they drew and interpret it as a depiction of what they meant to draw, even if it's not the depiction, a perfect depiction. It needs to be naturally interpretable, right? So I guess in both of these, they must be natural.
But there is a feedback loop there, which makes it much more complicated to describe what's going on. But thanks for your comments. I mean, those are interesting questions. I think now I'll move on to the second part, which is about a very different topic. And it's very, like, the actual results I'll show are very preliminary, but hopefully it's suggestive of interesting directions. And I want to talk about perceptual ambiguity, which I'm sure everyone here is thought quite a bit about. And I'll just motivate this with this is an example of an image which at first seems ambiguous. There's a frog in there, and once you see the frog, then it's hard to unsee. So I'm sure everyone here has seen many kinds of these hidden images and visual illusions. So I want to begin with two basic principles of perception and of making decisions, which are that certain images and scenes are ambiguous, and that we seek to resolve uncertainty because it is beneficial for navigation and survival in the world to gather information, and the promise of information is interesting. And so perceptual uncertainty, I think, is an important factor in these things, that you might, for some objects, after you have enough time to understand the scene, you have a peaked posterior probability distribution over the scene, what the scene identity is. For bistable scenes, you might have a posterior distribution which has two possibilities, which you can kind of jump back and forth between. And resolving these ambiguities helps for making decisions in the world, in choosing actions. And one other factor I want to observe is that viewing duration matters. So for an ambiguous scene like this, you might initially have this very vague probability distribution over the interpretation of it, and after some time, it may resolve into a much less ambiguous interpretation. And so within psychology of art, there's been some discussion around these different types of percepts and how they might relate to art. And there's one particular kind of ambiguity I want to discuss called visual indeterminacy, which is coined, this is a term coined by Rob Pepperell to describe scenes that seem at first like they ought to be interpretable. At first, this object might look like it's a simple object, but as you look further at it, it seems it doesn't resolve. You can't tell figure ground. You can't tell what the silhouette is. And this has been important in some form throughout art history, and also as the scene gets more complex, it becomes more interesting, I should say. So this is a phenomenon throughout art history. It really became, started to appear more significantly in the 19th century, for example, with Turner's works, and a lot of Turner's paintings seem like real scenes, especially knowing the title, this is a sunset, but resolving individual details is elusive. And within the modern art era, the notion of ambiguity and suggestiveness became prominent. So Picasso said that he thought that when looking at a picture, one should say that the more associations it can open up, the better. So it really became a value in itself in modern art that images should be ambiguous. They should suggest multiple interpretations without resolving to any individual interpretation. More simply, the contemporary painter Gerhard Richter, who's one of my favorites, has said, "I don't like pictures that I understand." And this is one of his paintings, which he calls Annunciation. Again, suggestive of a Renaissance artwork, but doesn't quite resolve into one. And he's actually, the painter, he's described this as a perceptual process. He said, "We only find paintings interesting because we search for something familiar. And usually we do find the similarities, table, blanket, and so on. When we do not find anything, we are frustrated, and that keeps us excited and interested." So there's this notion that we are intrigued by these kinds of artworks because we expect it, they seem like they ought to be interpretable, and yet they're not. So as I mentioned, there's been quite a few studies in the psychology literature which have begun to explore and analyze these kinds of phenomena. And I would recommend, as a starting point, this paper by Vendekreuz and Vagabonds is very nice, and work by Claudia Muth called Semantic Instability with good surveys and interesting studies of these. And the Vendekreuz really talks about this in the context of predictive coding and neural uncertainty. But a lot of this work, I think it's limited in two particular ways. It's really the ways I want to focus here are on the perceptual studies. The question is, where do you get good stimuli? And a lot of these studies, they have a set of artworks and of two classes of artworks, some that are ambiguous and some that are not, and then they ask in-person participants to say which ones are more interesting. And so there's not and it could be those confounding factors. Like in one study, they have Magritte paintings and Magritte paintings that they've modified in Photoshop, and maybe they're just not as good at Photoshop or as good as artists as Magritte was. There's a big question of how do you get good stimuli. And then the other question is, how do we measure ambiguity? So in all these studies, they ask people, is it ambiguous or not? Or is it interesting or not? And we'd really like richer descriptions that can emerge about these different categories and different types of ambiguities. And so there's a question of how we do that. And so I'll describe a preliminary approach towards addressing both these questions. So where do we get stimuli? Well, it turns out there's this really exciting set of work around generative adversarial networks, GANs, in the machine learning and vision world to generate images. These have been adopted by a set of artists who are making artwork using GANs. So for example, this is an installation piece by Mario Klingemann that was auctioned at Sotheby's, I think, for $50,000. And it's built on GANs. You walk up to it and it makes a version of your face, which is a little bit distorted through a GAN. And this is in pretty much any artist who is working with AI software these days in some form has experimented with GANs or done work with GANs. Here's work by Mario Klingemann and Trevor Paglen, who's a MacArthur Fellow, a fairly significant AI artist. Other more up-and-coming artists like Helena Sarin, Sophia Crespo. There's this whole community of artists who are experimenting with AI, and many of them have used GANs in some way. And I would argue that the GAN images that they are producing as art are visually indeterminate in the same way that we've seen in modern and contemporary art. And I actually think that this is a property of GANs, that when they work, sometimes style GAN FFHQ on faces, every face looks great. But when the GANs break down, when they are creating images that they're not quite capable of doing, they have this weird indeterminate kind of property that is very suggestive of modern art. It is as if they were designed to create this kind of modern art, even though they weren't. And I think there's a lot of interesting things we could discuss in the way that GANs compose elements of natural scenes to produce this property. There's some room for study there. And in fact, the GANs that are sort of most useful are not the best, highest quality images. So, 20, 30 years ago, we had texture synthesis methods like Portilla, Simoncelli, Hegerbergen, Efros-Long that were, pretty good at very restricted classes of scenes, but not great for making art. Like I mentioned, StyleGAN on faces looks great. Like you can just keep hitting resample over and over, and every face looks really real. And it's not that great for making art. At BigGAN, especially when you mess up BigGAN, which is a much more general class of image synthesis categories, it looks weird a lot. And it's much more indeterminate, much more interesting. And one way to experiment with this is with this website called ArtBreeder, which is amazing. I love this. If you have any interest in art, I highly recommend it. Artbreeder.com, you can check it out after the talk. And it lets you remix and explore the space of images produced by BigGAN in the general, quote, general model. And you just keep producing these images that just seem indeterminate and fascinating and interesting. And so it really kind of suggests the natural tendency of GANs to produce indeterminate images. And so in order to explore the perception, this work that we recently published, and this is work done by my former intern, Shi Wang. So this is all her work. And we wanted to start to see if we can quantify the different types of ambiguity. And so we formulated this crowdsourced perception task in Mechanical Turk, where we show a crowd worker an image for 3 seconds, and then ask them to give us a short textual description of the image. And so the responses we get for this image are white fluffy cat, white cat, and so on. For this image, we get much more varied descriptions: calm shell, robot-looking swan, giant snail. So you can see that the descriptions are all over the place. And so our main idea here is that this variability in descriptions will reflect perceptual uncertainty to some extent. So for example, if we just do the very simple text processing filter, so extract all of the nouns out of the descriptions and combine synonyms, and they plot the histogram. So cat was the most frequent word used to describe this image. And then there's a set of, and then some people mention its eyes, and there's some other nouns that each got mentioned once, and that's this other bar here. For the other image I showed, there's a much broader range of different terms people use. And then the other singleton terms were all over the place as well. And if we compute the entropy of these histograms, we see that this distribution is much higher entropy on the right than the one on the left. And so we'll use this entropy as a way to quantify the ambiguity or the complexity, or hopefully the perceptual ambiguity of the image. So we gathered a data set up from amongst the most popular images on ArtBreeder, and Rob Pepperell, our collaborator, who coined that term indeterminacy, visual indeterminacy, he categorized them as abstract or flat abstract, indeterminate, dichotomous, or recognizable. And so we can see that the images, something really going wrong with my animations here. I've never seen this before. Okay, let me just try. This is peculiar. The object's there, and no. Well, okay. This is. I'm sorry. I've never seen this. The best way to show these images are. Try one more thing. This is not great either. I'm sorry. I think I need to find the paper. This is so weird. So I'll just say, so we plot these images according to, show which images are most indeterminate or least indeterminate. And we see some interesting patterns are emerging. So the most indeterminate, these, let's see if I can try anything else here.
Aaron, what if you delete the animations?
There is no animation in this slide, which is
Oh,
R. And do I have this slide to any other talk? Yeah. Okay. Oh, sorry about this. Hopefully you can see this PDF. If not, let me know. So these are the images with
sorry,
the highest.
Aaron, we're just
share-
no, it's still.
Yeah,
Yeah.
sorry, you might have to share the actual PDF window. Right now, it's just the Keynote window that we're seeing.
Okay. Okay. You should be seeing it now.
Yeah.
Yes.
Okay. So these are the images in our data set which have the highest and lowest entropy. So the ones in the top, pizza, weird pizza, everyone agrees what these are. The ones in the bottom are clearly evocative of many different possible interpretations. So that's nice. And one interesting thing is we saw that the images with these sort of like very evocative ones came up with higher entropy than completely abstract ones. And I don't think those are in the PDF file, but like these abstract flat ones, which are sort of solid colors, they have lower entropy in their descriptions than these images, which have like suits, steelwork, suit of armor. So let me try to share my whole desktop. So I'm not, so there's no like desktop share here that I see. Unfortunately, I have to switch back and forth in what I share. So yeah, so these images have lower entropy than the indeterminate ones. So the next thing we tried was 2 different viewing durations. So for this image, if we show it for half a second, we get a different set of responses than if we show it for 3 seconds. In particular, in the 3 second, there's a whole bunch of more words that appear that weren't in the half-second condition. And so we can plot which images. Okay, so I'm now switching. Hopefully you are now seeing my PDF file. These are the images with high entropy that showed either the greatest increase or decrease over time. So all of them were ambiguous after 3 seconds. These images on the top became less ambiguous. So at first people are confused and then they sort of resolve into, people say alien or mask, there's one on the right. The images at the bottom here get more different descriptions over time. People's set of explanations get more richer. So we're starting to see sort of different categories somehow emerge from these tasks. These are images that were conversely not ambiguous or like low entropy after or medium entropy after 3 seconds. These images at the top decreased. So maybe at first people had lots of different descriptions for what this is. And after 3 seconds, they all basically say pizza. And the ones at the bottom tend to be more dichotomous. At first, you might just say mushroom for the fourth one over here. But then after a while, you might say it's a mushroom with eyes or a mushroom creature or something. And so, all right, I am switching back to sharing my slides. Okay, hopefully you're seeing my keynote now. So if we plot on 2 axes, the entropy after 3 seconds in the horizontal axis, entropy after half a second for the vertical axis, and then color by the initial categories that Rob produced, we start to see a segmentation here. The recognizable images all have low entropy under both conditions. The dichotomous images that sort of have 2 interpretations start out ambiguous and then decrease over increase, or start out with simple interpretations and increase over time. And the other ones are kind of mixed together. The indeterminate ones here are all mostly clustered at the top of the graph. So again, this methodology is starting to show us these different categories emerge. So to summarize, we believe that this variability in free-form responses can help to some extent measure indeterminacy, and that these categorizations begin to emerge from the data. Obviously, there's a lot of limitations I'm sure you've already recognized in what I described. Like in some sense, we're really measuring complexity. Like a scene, we can't distinguish between a scene which is a lot of recognizable elements versus one which has one element that could be many different things. And we're currently now working on relating these properties to aesthetic judgments. And so far we've found that one thing is that if we just ask people to rate images 1 star, 5 star, then basically everyone prefers the cats and the landscapes. They don't like the indeterminate images. If we give them a task where they have to spend more time with the images, where they have to first look at them and rate them and maybe write descriptions of them, then a subset of the raters actually prefer the indeterminate images. At least that's what it seems so far in our preliminary results. And we're still working on gathering more data and relating these things across different data sets and different types of images. So just to conclude the whole talk, thanks for your patience. I'm arguing that I think line drawing perception is a consequence of real image perception as a special case of how we perceive artworks in general, and with evidence from computer vision data and based on computer graphics models. I think that indeterminacy can be understood in terms of perceptual uncertainty. And in general, if we're talking about what makes artworks interesting or evocative or intriguing, we have to talk about perceptual uncertainty in the future. And there's a lot of room to explore this through the kinds of studies I described. And I think that a combined theory of perception art in general would account for these different things and build on ideas from computer vision and computer graphics. And more generally, this sort of computational model gives us insight into the perception of art. And with that, again, thanks for your attention and for your patience. And I'm happy to take further questions or comments. I'm opening up my Zoom window. Hopefully, let's see, I guess I can stop sharing. And okay, so I see one comment in the chat. What are other common hypotheses regarding the perception of line drawings? And honestly, I don't know of any that are really, either line drawings are learned or they are activating edge cells, or what I described. And I don't really feel like I've seen any other I just don't think there's any other story in the literature that seems compelling that I'm aware of at all.
Yeah, so thank you, Aaron. So just again to remind everyone, if you have questions, feel free to raise your hand, or you can post questions in the chat window as well. So I see Nick has his hand up, so why don't we go ahead and start there.
Okay. So if I was following right, we had occluding contours, suggestive contours, and surface markings as the three broadest categories of line. And would you say that the occluding contours and the surface markings are more kind of objectively determined, procedurally determined, and that this new system that you're building with ranking entropy is focusing on the suggestive contours? Do I have that right?
Oh no, the two parts of talk are completely separate from each other. So the indeterminacy stuff is like not directly related at all to line drawing. I mean, there is a relationship. Line drawings have perceptual uncertainty, and there's ambiguity in line drawings, but that's not really what the second part is about.
Okay. Well, as you were saying before, with the connection between line drawings and photographs, I worked on the Google Quick Draw project a few years ago, and no one expected the photo recognizing algorithm that it was based on, the cloud vision, to be able to recognize line drawings until it turned out that it could. And so that was just a huge, shocking moment for me a while back. And so it was really interesting to hear that kind of confirmed here. So all the discussion of ambiguity, investigation of ambiguity that you're doing could apply to line drawing. You're saying it's not limited to.
Oh, for sure. Yeah, I think line drawing is a really interesting special case because it seems so different from photographs and lots of other artistic styles. Like, it's sort of more obvious. I'm actually surprised to hear that Quick Draw worked well because so much of those are so abstracted. And like that was the sketch art and data set, I thought. And so like there's such a table is a circle with four legs, like four ovals coming out of it. I would not expect that natural image model to work on that. And if what you described is,
it was by cherry picking the results, right? So it's only looking.
I see. So there's like a more realistic image. That's more what I would expect. And if that's described anywhere, I'd love to see, like, if it's written down or that surprising result. I would love to see that.
I think Christopher was next. Chris?
Yeah, thank you, Aaron, for the fantastic talk. That was really, really good. I just have a very tangential question. I was wondering if much of the underlying principles that you've been focusing on for visual perception, if you guys have given much thought as to whether there's parallels in auditory or sound perception, or maybe other sensory modalities. I'm just wondering if, there's principles at play that translate more broadly in an multi-sensory sort of way.
Yeah, I absolutely do. I don't know much about audition. I think, this notion of ambiguity is throughout all kinds of art and sensing. Like in narrative forms like novels and movies. The most interesting movies are ones where and novels are the ones where you're wondering what's going to happen and wondering how to interpret what happened, and people have long discussions over the meaning or what was that character thinking. Ambiguity is very powerful as a cue. In terms of audition, the only thing I can think of which is sort of like really vaguely related is like Michael Lewicki had that work that showed how our auditory processing can be described through natural image statistics. And I guess, one tangent, when I hear music, often I sort of relate musical instruments to human voices. I hear a piano and I think of someone I know who has a similar voice. And I think there's a connection there. But those are some random comments.
Just really quick, James, are you waiting to ask a question, or is that just residual from the last session?
No, I was going to ask a question if I can.
Okay.
Yeah, great talk. Both parts super interesting. So on the second part, yeah, I see this problem of trying to discriminate between complexity and indeterminacy and sort of multi-modal interpretation. So I'm wondering if you think that if you had a kind of variational autoencoder or something, or GAN system where you could perturb the latent representation, if you would predict that images that are indeterminate would mean that a small perturbation would lead to a large change in, let's say, verbal description potentially, and that might differentiate from complexity, where maybe with the same size of perturbation, it wouldn't necessarily change the verbal description or something like that. Or can you think of any sort of creative ways of teasing apart? You can also do test, retest of the same individual, right? To tease these two things apart. Aaron?
Yeah, that's an interesting question. Two things for me. Oh,
you're back now.
Can you hear me now?
Yeah.
Yeah.
Okay, yeah, I just saw a message popped up that said my internet connection is unstable. Okay. We've thought about a couple different things. So I think the ideal answer would be better natural language processing, but I'm not. I don't know that area at all, and so my poking around it hasn't really been that useful, or we haven't found anything that really addresses that. We've also thought about applying a trained classifier to detectron type model to see how ambiguous computer vision model thinks the results are, the interpretation is. I think in terms of perturbing the GAN latent space, it's a really interesting question. There's the hypothesis that interpretations will generally be stable. That I would imagine that if you imagine the posterior distribution of our interpretations in an image is everything's very close, so you perturb the image slightly, then it's very easy for the most likely or your samples from that distribution to change. I can imagine that might work. All of these are kind of, it's hard to predict which of these are going to work. I also see a question in the chat that from Shayan Kashvari.
Before we get to that, I just want to make a quick comment. Okay. Since we're at the top of the hour, if anybody has to run away, of course, they're free to, but we'll keep going so long as Aaron is happy to answer questions. And also specifically to grad students and postdocs, there will be a session at the end if you'd like to have additional discussions or questions with Aaron afterwards. So please stick around. It'll be on the same Zoom meeting as we're on right now. So Anyway, yes, Aaron, there's a question in the chat. Please carry on.
Yeah, and yeah, so if you have to leave, thanks again so much for attending. And I meant to mention, like, my background is not in perception, so I'm definitely really interested to hear feedback or citations that you think are relevant. Basically, to answer the question, we are currently now trying to apply this entropy measure to Cubist and Renaissance paintings, that have been used in previous studies, so we can see how they relate to our data so far, and see how people's evaluations of them relate across these data sets. So I'm looking forward to seeing how that turns out.
And oh, Nico, you were going to ask a question or no?
Yeah, sure. No, if there's time, I do. Thanks, Aaron. Was very inspiring, and particularly the first part about line drawings got me back into got my thinking back into a question that I had often been carrying around with, but never had any good solution for, and you might have an idea. So I've been working with point light displays for a long time, as you may know, and
yes,
you were also dealing with human motion at some point. And point light displays have been fascinating people for a long time for all sorts of different reasons. But one thing is that they are so compelling on the one hand, but on the other hand, they are absolutely unnatural stimuli in many respects.
Mm-hmm.
So if you look at the special frequency spectrum, for instance, it's like those kind of spectra do not exist in the real world on the one hand. On the other hand, they represent something that strikes our visual system immediately. And line drawings do something different, or do something similar. So at least in some, on some statistical description levels, they are completely unnatural. They don't occur in the real world, and yet we respond to them so strongly. And I wonder how, what I can take from what you told us about sensitivity to line drawings into the domain of biological motion, where we deal with just a few high contrast, high special frequency dots.
Well, I guess I have a few responses to that, which I think are all completely unsatisfying. The first question is, if someone who is, if you ask someone who has never seen a picture before, or had never watched a movie, or seen modern technology, can they understand point light displays? I don't know if that's been studied or if it's worth the trouble. So one question is, to what extent is that ability learned? Which I don't think is very satisfying. And the other unsatisfying answer is that I think, it's like being able to recognize animal motion and human motion is really important for our survival, as well as our social interactions. And for predators and prey, they need the ability to camouflage and avoid gaze. And if you're walking through the jungle, the lighting conditions and camouflage and situation can be very, very complicated. I mean, think about the shadows cast by trees. So in that situation, there are motion cues that would be more robust than the lighting and shadowing cues, I guess. That's my only response. I don't know if that's at all plausible.
Yeah, sure.
Any other questions? Looks like there's some students will be back at 3:30, but we have a little bit more time. Oh, Nick, you see your hand up again. Excellent.
Yeah, the use of depth in one of the early examples you were showing. I've done some purely artistic experimenting with getting contours from Connect footage and varying what is generated from the RGB and the depth sources calibrated. Can you talk about how you got to the finished drawings derived from the depth in your examples? Were those the pairs that were given to your neural net, drawing and depth map?
Well, the neural network is trained by somebody else, and I just downloaded the trained model from the web. They trained it on primarily supervised pairs of photographs and depth maps. I think it's a little bit more complicated than that, but that's it. That's close enough. And then I just took that trained network and fed it a line drawing.
Oh, okay. So that was finding depth in the drawn images. So that was able to use the same.
Yeah, that's right. Yeah.
Same way. All right. Thanks. I looked up, double checked the Quick Draw paper did not discuss how they got the images, the original images, by which they determined which people's rounds playing the game were winning. And it was purely trial and error, if I can recall, to find the ones that the cloud vision system could recognize from its being trained on photos, even though they were drawing. So I guess kind of the same principle as that perspective experiment.
Okay, thanks.
I'll ask a quick question since we're on the topic of that particular experiment. There's been, as I'm sure you're probably aware, Aaron, there's been a number of papers that have talked about whether or not, modern networks are actually recognizing shape or are instead kind of latching on to other perceptual cues. And so I'm actually really surprised that that depth estimation worked at all on line drawings in light of a lot of the recent work that's been studied where people do things like, randomize the texture of objects and scenes, but otherwise maintain shape and show how performance degrades. And I was just wondering if you had any kind of thoughts on how to reconcile those two results. Is it because of the depth estimation task that is somehow more sensitive to shape instead of texture, or is there something else going on that you might speculate on?
Well, I think that those results were for classification tasks, which is arguably require you're fewer bits of information than that than in depth estimation. Yeah, but I mean that's my only guess.
So you think if you took the line drawings and fed them into, it's as a thought experiment, I think the answer is obvious, but presumably if you took the line drawings and fed them into, ResNet, whatever, for, trained on ImageNet for recognition, you would expect failure? Is that?
Yes, I think so. We did, I would expect failure, yeah. And I think it does make sense that, texture is such a strong cue for image category, whereas it's not as strong a cue for things like object silhouettes. Mm-hmm. It's definitely a very relevant cue for object identity, which is a cue for shape, but to get depth, you need a lot more than just texture. And there are other cues which are probably stronger than texture that the depth network is using, I would guess. Like local shading, for example, and silhouette shape.
Can I ask a question?
Yes. Sorry, James, I keep forgetting whether or not that's a new or not in yours.
Actually, Aaron, I was wondering if you could put those that slide up again that showed the output of the Lassinger single view 3D algorithm to your line drawings, because I think
which slide?
The slide that shows the range map produced by the Lassinger algorithm, a single view 3D algorithm on your line drawings. So yeah, I just was interested because it's possible to visually trick ourselves that the algorithm's doing better than than it really is. Like, so for example, if you look at the bottom picture, the overwhelming thing is that it's carved out the sky and there is a gradient from the bottom to the top, that gradient is a really important contribution to the proportion of variance captured by most single view 3D algorithms. So I guess my question is kind of how much is really going on here, and these are, so in addition to the sort of top to bottom gradient, the other cues could be quite local, perhaps, I wonder. So yeah, just as a general question about maybe there isn't such a contradiction in the sort of Betke results about, the dominance of texture and these results. It's not clear that the system is pulling out global shape, maybe. What do you think about that?
Yeah, I think it's hard to draw precise conclusions. I think, my main point here is simply like qualitatively, like roughly the overall results are comparable and qualitatively pretty accurate as compared to the natural images. I think it isn't something that's just simple. It's not like, more texture means more depth, because clearly that's not what happens here. Like there's a dark black line here, which is close, and it made a mistake over there, but there's other dark black lines which weren't made close. Like I don't think there's like a very simple explanation that explains these results. Texture might certainly be a factor here.
Couldn't you just say there's a bottom to top gradient, and then there is an ability to ignore the sky, that's important, or to find that contour that separates the sky. And then for sure the lamppost is seen as an occluding object, the front one, not the back one. But you could imagine that, units at an intermediate convolutional layer that are picking up that vertical bit of contour without a real global computation.
So yeah, there's certainly a lot more you could explore here. I think those arguments don't explain the portrait in the upper left there. Let me see if I can find my notes. So yeah, this is clearly not fully explored what's really going on, but I think, given the network, it wasn't even trained for this. Like it wasn't like I fine-tuned the network for this task, or and I have a few other scenes. Let me see if I can find where I put that.
Yeah, the portrait.
So generally I found like outdoor scenes and certain kinds of indoor scenes, it worked pretty well. And there's like a whole class. Yeah, sorry, I don't have my images on hand or readily available.
Well, it is capturing, so in that scene you're pointing at now, it is successfully capturing some of that right to left gradient on the buildings on the right, right? So it's certainly capturing like wall structure to some degree.
You could actually measure how well it's doing if you really wanted to, given some of the line drawing rendering algorithms. You could actually take synthetic scenes and render them and actually compare the depth maps, but I'm not sure what it would really tell you at the end of the day.
Yeah.
So there was a quick question in the chat in terms of following up with you afterwards, Aaron, if there are other questions or comments that people have. I don't know if you have a preferred method of contact for such things.
Sure, yeah, email. You can find it on my webpage. I'll put it in the chat. I think that's probably the easiest way to get in touch.
Okay. And so I thank you, Aaron, again for the fantastic talk and for tolerating everyone's questions. We are going to have, just as a reminder to everyone, there is going to be a training meeting session. To give Aaron a little bit of time, let's make that start at, say, 3:40, so in about 15 minutes, so that Aaron can get a bit of a break from talking, because he's been going nonstop for the last hour and a half. And to give everyone else a chance who needs to go run off and get some water or what have you. So again, thank you, Aaron, so much. It's great hearing about what you've been working on, and yeah, good to have you.
Great, yeah, thanks so much. Yeah, it's been really fun.
Thanks, Aaron, that's great.
I'm going to keep the meeting open for people to come back.
Thanks, Aaron.
Great.
I really like your, you got the Edgar Allan Poe look going on. It's great. It suits you well.